Hello, welcome to our channel for rprogramming. In this video, we will briefly talk about chi-square distribution and chi-squaretest and show how to implement chi-square distribution and test in rprogramming. So we know chi-square distribution is a continuous distribution with degrees of freedom. It is used to describe the distribution of a sum of squared random variables. So it also used to test the goodness of fit of a distribution of data, whether data series are independent, and for estimating the confidence interval for the variance of random variable. So say one, say two, say n are independent standard and normal random variables. So they have mean 0 and standard deviation 1. So the random variable x, which is the sum of the square of those standard and normal random variables, will follow a chi-square distribution with n degrees of freedom. So we use the notation chi-square distribution here. So this figure shows several curves for the chi-square distribution's density function in terms of different degrees of freedom. So for example, this green curve k equals 2, this one, and you can see when the degrees of freedom becomes larger and higher, and the curve will be more symmetric and will have a bell shape. So it will approximate to normal distribution when degrees of freedom will be very large. So in the application, in the regression, we know SSR, which is the sum of squared residue divided by unknown variance of the data, have a chi-square distribution with n minus 2 degrees of freedom. And in the independent test of two categorical variables, so the test statistic, this statistic, which is the opposite of the cons minus the model, the cons take square divided by the model cons, this statistic will have chi-square distribution with r minus 1 times c minus 1 degrees of freedom. So where r and c represent the column number and the row number respectively. So column number and the row number actually are the values, categories of two categorical variables, right, in the table. And for the density of the chi-square distribution will come from a gamma distribution. So gamma distribution is the fundamentals of many distributions in statistics. Gamma distribution has two parameters, alpha and beta. So its density function is given by this formula. Beta alpha, gamma alpha, 1 divided by this term, then times the x alpha minus 1 in power times e minus x divided by beta in power. So gamma distribution is a variable larger than 0. So this is why chi-square distribution also larger than 0, because chi-square distribution models the random variable's power, a square, is larger than no negative value, right? And both alpha and beta are positive parameters. So if we let alpha equals v minus 2 and beta equals 2, so a gamma random variable will become as chi-square random variable. So chi-square distribution has this formula in the density function. So 1 divided by the part, this part equals 2v minus 2 in power, then times a gamma function v minus 2, then times x v minus 2 minus 1 in power, then times e minus x divided by 2 in power for the random variable positive, and 0 for the negative value. And the gamma function is an integral of x alpha minus 1 in power times e minus x in power. Take integral over dx. And the mean of a chi-square distribution is its degrees of freedom. So if we look at previous pages, how many random variables square summation. So there are how many, which means these degrees of freedom. For example, we have n squares, n random variable of square of a standard normal distribution's random variable. Then here the distribution has degrees of freedom n here. And the variance of a chi-square distribution actually is 2 times v. So this table and this curve is used to manually do a chi-square test or calculate chi-square distribution. So if we look at this alpha shaded area and this value x, this value is actually the critical value of a chi-square distribution, or with a quantile value. So which will chi alpha, which means it will leave the shaded area represents the probability to this area as alpha. Let's say if alpha we set is 0.05, so this critical value is a chi-square 0.05 with respect to specific degrees of freedom. So if you look at this table, v is here, for example, v equals 5, then this value 0.831, and this alpha 0.975, which means alpha 0.9375, almost here, right? The shaded area will be from here to here is 0.975 because the total area is 1. So this critical value will be here like 0.831, right? And the chi-square test usually will aim to find the critical value in the data. So if this critical value higher than this assumed critical value for 0.05, so we say this test is significant. Or if we get a p-value less than this alpha 0.05, so we can also say this test is significant, right? So we will test if the p-value area larger than critical values area, right? So in R programming, usually we will use dpqr, one of these alphabet, then with the abbreviation of a distribution to do calculation in statistics. So D for density, and P for the cumulative probability, and the Q for the quantile function, and R is for the random number generation. So specifically for chi-square distribution, we just use D chi-square, P chi-square, and Q chi-square, and R chi-square. So next we will show examples in RStudio to implement chi-square distribution. So now we go to RStudio. First function for the chi-square distribution is d chi-square. It's very simple. We just define a variable vector for critical value or random variable in chi-square distribution and set the degrees of freedom. Then the density for each value will be calculated. So we set degrees of freedom is 10 here, and a vector from 1 to 20. We'll print sentence. Then we can calculate calculate the chi-square of this vector. This value 10 value, these 20 values represent the density of each random variable in chi-square distribution with degrees of freedom equals 10. So next we can also plot. So sketch plot for these 20 values. This is very close to the shape of a chi-square distribution with 10 degrees of freedom. So the next function called Q chi-square, so which means to calculate a critical value in terms of a cumulative probability. So we set the freedom is 5 and set the p. This is the, if we look at this curve, the p here, the p cumulative probability is actually the white area, is 1 minus alpha. So here the white area is 0.05 because Q chi-square accepts a cumulative probability. It's 1 minus alpha in the figure. So we set 0.75. Show how it's going. So critical value is about 6.62. So which means in this chi-square, this white area is 0.75 and this critical value is 6.62. So next function is p chi-square. It is actually the opposite operation of q chi-square, because here we set the degrees of freedom and using p chi-square to calculate a critical values cumulative probability. So which means we calculate the probability for all random variables less than this value. So if we look at again this figure, so for the p chi-square, we will calculate this white area probability. This is the cumulative probability for all the random variable less than this critical value. So we calculate the cumulative probability for all the variables less than 5, or say between 0 to 5, because all the chi-square variables are larger than 0. So this probability is about 0.584. So which means this white area is 0.584 and this critical value is 5. So the last function is called r chi-square. It is very easy to understand. We just generate random numbers from a chi-square distribution. Because chi-square distribution has degrees of freedom 5, so we create 50,000 of such random variable. You can also plot in a histogram. Here we set frequency false, so which means to show the density, not the frequency. So this shape is the same no matter you set a counts or density. This is very close to a, because it's a very large number, 50,000, so very close to a real exact chi-square distribution with degrees of freedom 5. Next, we will show an example to do chi-square test. So the chi-square test of independence evaluates whether there is an association between the categories of the two variables. So we will take the survey data in a math library, which represents the data from a survey conducted on students. So we load this library first, and we show the data called survey. So survey data actually is a data frame with 237 observations of 12 variables. So we are particularly interested in testing the hypothesis whether the students' smoking habit is independent of their exercise level at 0.05 significance level. So we create data frame, just take two variables, smoke and excesses, from data frame survey. So students data has two variables. We just use a table survey, or we can create a student's data with just a table function for these two variables. Next, we can print out this table. So this is a contingency table for the two variables, all the value, because the smoking, frequency, non-sum, and heavy, and exercises, they have 3 values. So totally we'll have 12 fields in this table. Next, we can just use chisquaretest function of this contingency table. We can just omit this warning message. The result, get p-value 0.48 and has a chi-squaretest statistic 5.48 with degrees of freedom 6. So because the p-value here is larger than 0.05, so we conclude that the smoking habit is independent of the excess level of the students, and there's a weak or no correlation between the two variables. So because the p-value is 0.48, so alpha is 0.05, so which means the critical value from this test is less than this critical value, right? Less than the critical value which will be significant level. So we'll stay here, critical value. This is about 0.48 for this area, for the shaded area. So the test is not significant. You can also find the source file and data files in our website here. Thanks for watching and subscribing our channel.